Today in DC electrical circuits, we're going to take a look at lab number 12, maximum power transfer. The objective of this exercise is to determine the conditions under which a load will produce maximum power. Further, the variance of load power and system efficiency will be examined graphically. Under reference sections, I'm referring to Holmes Outlines, Basic Electricity, 2nd edition. We're going to be looking at chapter number 9, Network Calculations and Maximum Power Transfer. So according to Holmes Outlines, the maximum power is supplied by the voltage source and received by the load resistor if the value of the resistor equals the value of the internal resistance of the voltage source. For maximum power transfer then, RL equals RI. In our theory overview, it says in order to achieve the maximum load power in a DC circuit, the load resistance must equal the driving resistance, that is the internal resistance of the source. Any load resistance value above or below this will produce a smaller load power. System efficiency, we use the Greek letter eta for, is 50% at the maximum power case. This is because the load and internal resistance form a basic series loop, and as they have the same value, they must exhibit equal currents and voltages, and hence equal powers. Under equipment, we're going to be using the Agilent model number E3630A power supply. I'm not going to bother with its serial number. The digital multimeter is going to be the Mastec MSM 9803. I'm not going to bother with its serial number. My 3.3 k ohm resistor was measured as 3.260 k ohms, and my 100 k ohm potentiometer actually measured 100.6 k ohms. Now keep in mind that's between point A and point B. We're not measuring to the wiper arm because that's the variable part of our resistor. The schematic for today's circuit is fairly simple. We're just going to be using a variable power supply, a fixed resistor, and a potentiometer for our load resistance. I've given you a place to do your sample calculations. So under procedure, step number 1, we're to consider the simple series circuit of figure 12.1. We're going to be using an applied voltage of 10 volts, and RI is going to be 3.3 k ohms. RI forms a simple voltage divider with RL. The power in the load is equal to VL squared divided by RL. And the total circuit power is E squared divided by RI plus RL. The larger the value of RL, the greater the load voltage. However, this does not mean that a very large value of RL will produce maximum load power due to the division by RL. That is, at some point, VL squared will grow more slowly than RL itself. This crossover point should occur when RL is equal to RI. Further, note that as RL increases, total circuit power decreases due to the increasing total resistance. This should lead to an increase in efficiency. An alternative way of looking at the efficiency question is to note that as RL increases, circuit current decreases. As power is directly proportional to the square of current, as RL increases, the power in RI must decrease, leaving a larger percentage of total power going to RL. So from procedure, step number 1, we can see that our load voltage is going to be equal to RL over RL plus RI times our applied voltage. Our load power is equal to VL squared divided by RL. Total power is equal to E squared divided by RI plus RL. And finally, our efficiency is power in the load divided by total power times 100%. And the efficiency calculation came from the theory overview, where it says efficiency is equal to the ratio of load power divided by total power times 100%. So under procedure, step number 2, it says using RL equal to 30 ohms, compute the expected values for load voltage, load power, total power, and efficiency, and record them in table 12.1. So using the formulas we obtained from procedure step number 1, we can see that the load voltage is equal to 30 ohms, which is RL, divided by the 30 ohms plus the 3.3K, and we're going to assume that 3.3K is the internal resistance of our circuit. We multiply that by the 10 volts supplied to our circuit, and that should equal 90.09 millivolts. The load power is going to be equal to 90.09. That's the voltage that we just calculated. We're going to square it and divide it by RL, which is 30 ohms. And that should work out to 270.541 microwatts. Remember, that's times 10 to the power of minus 6. Total power is going to be equal to the applied voltage squared, so that's 10 squared, divided by the 3.3K plus the 30 ohms from the load resistor. So that should equal 30.03 milliwatts. Finally, to calculate efficiency, we're going to take the load power, the 270.541 microwatts, and divide it by the total circuit power of 30.03 milliwatts times 100. And that should equal 0.9%. So in table 12.1, for RL equal to 30 ohms, VL is 90 millivolts, PL is 270 microwatts, PT is 30 milliwatts, and our efficiency is 0.9%. So continuing on under procedure, step number 2, it says repeat for the remaining RL values in the table. For the middle entry labeled actual, insert the measured value of your 3.3K ohm resistor used for RI. So in table 12.1, I've calculated VL at each of the resistances that were given to me. For the actual, I used 3.3K ohms, and you can see when you use exactly 3.3K ohms, VL is equal to 5 volts. Now I'm going to leave you to calculate power in the load, total power of the circuit, and the efficiency at each of these resistances. I gave you an example on the first line using 30 ohms. Now, whenever you're doing repetitive calculations, you can always use an Excel spreadsheet to help you do these calculations a little more quickly. I'm going to give you a little demonstration on how to do that now. So I want to go over how to use Excel to do all your pre-lab calculations. So you can see in here I have RL, VL, PL. So all of these were calculations. And if I click on cell C4, you can see up here in the formula bar there is a calculation for each of these cells. So in order for me to display the formula, I've put a little tick mark in front of the equal sign so that it shows up. And to put the formulas in, you notice in Excel you can't just write a formula in. I've used the ink equation editor to insert the formula so that we can see what the formula looks like. So for VL, you can see it's equal to RL divided by RL plus RI times E. And the formula is B4, because over here in B4 I have my value for RL. RI is a fixed resistance and E is a fixed voltage. So I've just typed those in the formula. So I'm going to show you how to set this up in Excel now. So I want to show you how easy it is to do your pre-lab calculations in Excel. So the first thing I'm going to do is come over to the B column and go down to position number 3. And the first thing I like to do is label my columns. So my first column is going to be RL. My next column is going to be VL, followed by PL, and PL is going to be in milliwatts, so I'm going to label it as MW. Next column will be total power, so that's PT, and that will also be in milliwatts. And then my last column is going to be efficiency. Now what I'm going to do is highlight each of those cells, and I want them to be centered. I like the font to be a little bit larger, so I'm going to increase it to 14. And I like it to be bold. Now you'll notice some of these headings are a little too large for the column. So I'm going to highlight the columns that I'm using. And then when I do a right click, I can come down to column width. And I'm going to change those widths to 15 and say OK. So now you can see I have a little more space. Now I like to box in each of my column headings. So I come up here to bottom border, and if you click on the borders icon, you can go to a thick outside border. So I like to do that for each of my column headings. Now under the RL column, I'm going to put in my resistor sizes that I'm going to be using for RL. So I start with 30, 150, 500, 1000. Now notice I'm not putting in 1K, I'm putting in 1000 because I need to use these numbers in the formula. So 2,500, 3,300, 4,000, 10,000, 25,000, 70,000, and 100,000. Now I like to have commas between my thousands, so what I'm going to do is hold down the left mouse button and highlight all of those cells. Then I'm going to do a right click, come down to Format Cells, and under the Number tab I'm going to select Number. Decimal places, you notice these are all whole numbers, so I don't want any decimal places, but I do want to use the thousandths comma, so I'll click on that. And then I click on OK. So now you can see whenever my number is greater than 1,000, it puts in the comma. So I can see that 100 k ohms is 100,000. Now we're going to calculate VL, and VL is equal to RL divided by RL plus R internal times the applied voltage. Now rather than typing this all in on my calculator, I'm going to use Excel. And to write a formula in Excel, you click on the cell you want to put the formula in. So this is C4. Just do a left click. Then you can start typing in your formula. Your formula always starts with an equal. Now we want RL, and RL is in column B4, so I can use the arrow key on the keyboard to move over, and you'll notice it highlights B4 and puts it in after the equal sign. So now I want to divide that, so we use the slash key on the keyboard for division, and in brackets we want RL, so I can use my arrow key to highlight RL, plus R internal. Now R internal is 3,300 ohms. So I'll just type that in. I'll close my bracket, and then I want to multiply that, so we use the asterisk off the keyboard, that's Shift 8, and I want to multiply it by the applied voltage of 10 volts. So when I'm happy with the formula, I can press the Enter key, and it puts the number in for me. If you want to edit the formula, you have to highlight the cell and edit the formula up here in the formula bar. Now it's put in more decimal places than I want, so I right click on the cell, come down to Format Cells. Once again in the Number tab, I'm going to select Number. And I think 2 decimal places will be sufficient, and I'll use the comma separator for the thousands. So then I'll click on OK. Now I'd like this centered in my column. So that is the answer for VL with an R load of 30 ohms, 0.09 volts. Now on a calculator, you'd have to do all those calculations all the way down. In Excel, I just do a left click to highlight the cell, right click, select Copy, then go to the cell I want to copy it into, hold down the left mouse button, and drag the cursor all the way down to the last cell I want the formula copied to. Then come back up to the first cell I want to copy it to, do a right click, paste, and you can see it's put the formula in for each of the cells and given me the answer. So if I click on one of those cells, you can see it's put in the formula, as B13, which is the next RL that I want to calculate VL for. Now to do the calculation for power in the load, that's VL squared divided by RL. So in this case, I click on D4, I type in equal, and I want VL squared, so I use the arrow key to go over to VL. To square it, I press Shift 6, and that puts in the little upper caret. That's for putting it to the power of, in this case it's the power of 2. So that's VL squared. I want to divide it by RL, so I can use the cursor to move over to RL, which is 30. Now this is going to calculate it in watts. I need it in milliwatts because watts will be far too small and have far too many decimal places. So I multiply it by 1,000, and that will give me my answer in milliwatts. So I'll press the Enter key, and here you can see my answer is 0.27 milliwatts. So I'm going to format the cell. So I go to right click, Format Cell. Once again, I want to go to the Number tab, Category Number, Number of decimal places, 2, and I want to use the comma and click on OK. Once again, I would like this centered in my column. Now I want to do the calculations for all the load resistances. So I highlight the cell, right click, copy, highlight the cells I want to copy it to, right click, paste. So it's a lot quicker using Excel to do all your pre-lab calculations when you have a lot of them to do. The next formula is for power total. So this is E squared divided by RI plus RL. And once again, it's in milliwatts, so I'll multiply it by 1,000. So I start by pressing equal. E squared is 10, Shift 6, 2, so that's E squared, divided by bracket, RI is 3,300, plus RL, I'm going to use the arrow key to move over and select B4, close my bracket, and then multiply by 1,000 to get back to milliwatts, and then press the Enter key. So once again, I need to format this cell. And center the total power in the column. Once again, I highlight the cell, right-click, copy, select the cells to copy to, right-click, paste. So there's all my total powers calculated for me. In the last column, I want efficiency. And efficiency is power in the load divided by total power times 100%. So in this case, I press equal. I'm going to go over to PL with the arrow key. I'm going to divide that by PT, select that with the arrow key, and then I'm going to multiply by 100 and press Enter. Once again, I need to format the cell, so right click, Format Cell. In this case, I click on Number. I think 1 decimal place will do, and I'll use the separator and click on OK. Once again, I'm going to center it in my column. Right-click, copy. Select all the cells. Right-click, paste. So these are all my Prelab calculations. So I'm going to label it calculated values. So in cell B2, I'm going to type in calculated. Once again, I want it to be in a larger font. I like it to be bold. Now I want to center it across all of these columns. So what I do is I highlight all of the columns. And then I come up to this icon here, which is merge and center. And you can see it centers it for me. And then I want to do a thick outside border around it. So there is my Prelab calculations ready to be used. Now under procedure, step number 3, we're to build the circuit of figure 12.1 using E of 10 volts, RI of 3.3 K. Now it says use a fixed resistor or potentiometer for RL and set it to 30 ohms. We've used potentiometers before. Remember, we're going to use either A or B and the wiper arm. So we're not going to go from end to end because that's the total 100K ohms. It says to measure the load voltage and record it in table 12.2. Then we're to calculate the load power, total power, and efficiency, and record these in tables 12.2. We're then to repeat for the remaining resistor values in the table. So in table 12.2, for our measurements, I've said use the closest fixed resistor size in your kit or use a potentiometer. So for the first case where they want 30 ohms, your closest resistor size in your kit is 47 ohms. Regardless, if you use a potentiometer, make sure you measure the resistance first and record it because we need that for the power calculations. So this is my circuit wired up on the trainer, and you can see the red terminal or the banana lead from the power supply, the plus 20 volt output, set to 10 volts, comes in and goes to my 3.3 k ohm resistor, which goes to the top of my potentiometer. The black lead goes to the center of the potentiometer, and you can see right at the bottom here there's nothing plugged into the bottom of my potentiometer. So that lead goes back to common of the power supply. The yellow lead is so I can measure the voltage between the 3.3 k ohm resistor and the first leg of the potentiometer. So setting your potentiometer to 30 ohms is very tricky, so you might want to use the 47 ohm resistor that came in your parts kit. My load voltage at 30 ohms is 89 millivolts. So in table 12.2, for RL, actual 30 ohms, my measured VL is 89 millivolts. So continuing on under procedure, step number 3, it says repeat for the remaining resistor values in the table. Setting your potentiometer to 150 ohms is going to be difficult, so you might want to use the 150 ohm resistor in your parts kit. At 150 ohms, my voltage reading is 0.438 volts, or 438 millivolts. At 500 ohms, my voltage reading is 1.338 volts. At 1K ohms, my voltage reading is 2.36 volts. With my potentiometer adjusted to approximately 2.5 k ohms, my voltage reading is 4.28 volts. Now I'm adjusting my potentiometer to get as close as possible to the 3.255 k ohms that I measured. I'm getting 3.26 k ohms, close enough. My voltage reading is 5.02 volts. At approximately 4 k ohms, I'm getting 5.61 volts. At 10 k ohms, I'm getting 7.6 volts. At 25 k ohms, I'm getting 8.89 volts. At 70 k ohms, I'm getting 9.59 volts. At 100 k ohms, I'm getting 9.72 volts. So in table 12.2, I've given you the option of either dialing in the exact resistance that you need to get using the potentiometer or the closest fixed resistor size. Regardless, whichever method that you use, make sure that you measure your resistance and write it down, because we're going to need it to calculate power. So in table 12.2, under VL, my 30 ohm resistor, my potentiometer was 31 ohms, and I measured 89 millivolts. For 150 ohms, I measured 149 ohms, and VL was 432 millivolts. For 500 ohms, I measured exactly 500 ohms, and VL was 1.338 volts. For 1 k ohms, I measured exactly 1 k ohms, and the load voltage was 2.36 volts. For 2.5 k ohms, I measured 2.486 k ohms, and the load voltage was 4.28 volts. For the actual resistor that I was using, it was 3.260 k ohms, and I measured 5.02 volts. The 4 k ohm resistor was 4.14 k ohms, and the load voltage was 5.61 volts. The 10 k ohm resistor, I measured 10.39 k ohms, and the load voltage was 7.6 volts. For the 25 k ohm resistance, I measured 25.27 k, and the load voltage was 8.89 volts. For the 70 k ohm resistor, I measured 70.1 k, and the load voltage was 9.59 volts. And lastly, for the 100 k ohm resistance, I measured 100.6 k ohms, and the load voltage was 9.72 volts. I'm going to leave you to calculate load power, total power, and efficiency. I would recommend that you use the Excel spreadsheet. It'll work a lot quicker for you. So now I've done all my lab measurements. I'm going to show you how easy it is to duplicate all our pre-lab calculations and use it to do our post-lab calculations. So I'm going to highlight everything we did previously, right-click Copy, move over to an unused area, and do a right-click Paste. Now I have to change my column widths again, so I'll highlight them, right-click, column width, 15, OK. Now this is no longer calculated, so I'll change it to measured. And RL is now going to be our measured resistance. So that was 31, 149, 500, 1000, 2,486, 3,260, 4,140, 10,390, 25,270, 70,100, 100,000, and 600. Now VL originally was a formula. Now we're going to put in our measured value of VL. So that was 0.089. And you'll notice because I've got it set to 2 decimal places, it automatically rounded up to 0.09. The next one was 0.432, 1.338, 2.360, 4.280, 5.020, 5.610, 7.6, 8.89, 9.59, 9.72. So because the column is automatically rounding up to 2 decimal places, you might want to highlight that column, do a right click, format cells, and change that to 3 decimal places, since we did measure 3 decimal places to begin with. You'll notice all the other columns have redone the calculations for you. You did not need to re-enter those calculations. You can go to the cell and check it, and you can see the formula has changed to J4 squared, whereas before it was C4 squared. So by copying all the cells over, it automatically readjusts for the columns that we're now using. So this makes work a lot easier for you doing your measured calculations. Under procedure, step number 4, we're to create a plot of the load power versus the load resistance value using the measured data from table 12.2. For best results, make sure that the horizontal axis, that's for RL, uses semi-log scaling instead of linear. So this is my graph of load power versus load resistance, and I've labeled the title at the top. On the horizontal axis, I have load resistance in ohms, and you'll notice I go 100, 1K, 10K, 100K, since this is a semi-log scale. On the vertical axis, I have load power, and it's in milliwatts. So I go 2 divisions is equal to 1 milliwatt. So 1, 2, 3, 4, 5, 6, 7, 8, 9 milliwatts. I've plotted my points from my table and drawn in the best fitting line that I could. Here I've drawn load power in milliwatts versus load resistance and used Excel's graphing feature to make the graph for me. Now I want to show you how to use the graphing features of Excel to help you plot load power in milliwatts versus load resistance. So the first thing we're going to do is select the data that we want to graph. So start with RL and highlight all of the column headings and all of the data. So this is what we want to plot. So we're going to go up to Insert, and we want to insert a graph or a chart. So this kind of chart that we're going to plot is called a scatter, XY, or bubble chart. And if you click on the little arrow by the icon, it brings down all the different charts. Now if you run the mouse over one of those charts, it will show you what it looks like. So we're going to select the second one, which gives us a curved line. So now we have a nice looking chart. You can position it anywhere on the screen that you like. You can double click on the chart title, and you can change the chart title to anything you like. So I'm going to call it Load Power. And remember, that was in milliwatts versus load resistance. Now the only problem with our chart is it's displaying everything from each of these columns. So if you come over to this icon here, you can go to Chart Filter. And you can see we can select what we want to plot. You'll notice RL comes up in one color because that's the bottom axis. So we don't want to plot VL, so you can deselect it. We want PL, we don't want PT, and we don't want efficiency. So then we can select Apply. Now we wanted this to be on semi-log scaling. So if you double click on the bottom axes, you can see we get Format Axes come up on the right-hand panel. So we're going to go down here till it says Logarithmic Scale. Select Logarithmic 10. Now you'll notice it starts way over here. So our minimum we're going to set to 10. And our maximum we're going to select 100,000. So this is the plot. Load power in milliwatts versus load resistance. And you can see it's on a semi-log scale. Under Procedure, step number 5, we're to create a plot of the efficiency versus the load resistance value using the measured data from Table 12.2. It says for best results, make sure that the horizontal axis for RL uses a linear scale. This is my graph of efficiency versus load resistance. And you can see the horizontal axis is a linear scale. It's resistance in K ohms. So I've gone 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 K ohms. And efficiency is in percentage. So I've gone 5, 10, 15, 20, all the way up to 100%. I've plotted in my points from the table and drawn in the line as best fitting as possible. Here I've plotted efficiency versus load resistance, and I've used Excel to draw the plot for me. So I want to show you how to do that now. Our next plot is efficiency versus load resistance. So once again, I'm going to start by selecting my column headings and all of my data. I go up to Insert, and I want to go to Chart, Scatter Chart, and I want the second one over, Scatter with Smooth Lines and Markers. Once again, you can move it anywhere on your page. I'm going to start by editing the chart title. So in this case, it's efficiency versus load resistance. Clicking on my chart, I'm going to go over to the chart filters. And in this case, I only want efficiency. Click on Apply. Now this is our standard scale. You'll notice it goes up to 120. If I click on the horizontal scale, I can go up to my minimums and maximums, and instead of 120,000, I'm just going to go to 100,000. So there's my chart for efficiency versus load resistance, and it's drawn in nicely for you. Now you can select the areas that you want to print. So if you want to print this particular area, you can highlight it. Go to File, Print, and you can either print the active sheet, entire workbook, or print selection, which is what we're doing, and then you can press Print. On the last page of the lab, I have 4 questions for you to answer based on your calculations, your observations, your conclusions, and your graphs. When you've completed your lab, leave your circuit set up on your trainer so your instructor can verify its operation, and they will initial your lab to indicate that it is complete.